This video is all about forces and more specifically about a certain type of diagram that we use to graphically represent all of the forces that are acting on a system. So this video is going to teach you about what a system is, how to draw this diagram, and then how to use this diagram. So just to remind you, a force is an interaction between two objects. There are different types of forces. We talked about contact versus non-contact forces before. For example, the gravitational force is a non-contact force between objects that have mass. But a force is always an interaction between two objects. So we like to use subscripts to describe those two objects and to identify who is exerting the force and what the force is acting on. So that's what the two subscripts represent. The first subscript identifies who exerted the force. Second subscript explains who is receiving or who that force is exerted on. So in this picture here, I see the force of the wall on a person as compared to the force of the person on the wall. So it's really important to name your forces. I like to use a capital F to describe every force, and then to use these subscripts to show the origin and then the receiver of the force. You may see variations on this, but the subscripts are always very important to do. So let's do an example here. I have a scenario where I have two dogs. So these are my two dogs. There's Hank is the black lab, and then Xena is she's a pit bull basset hound. And let's say Hank is laying on that carpet. Xena comes over and sits on top of him. They're both like on the floor. We're on my house that's on the surface of the earth. That's kind of the scenario that you're considering in this picture. So we want to identify the various interactions between all of the things that are in this scenario. So there's lots of different objects that are in this scenario. Let's just try to name a few of the interactions of the objects that are within this picture. So again, I'm not going to name everything. There's a lot of stuff going on. Let's just try to name a few of them. So maybe we can start off with just some contact forces. I see that Xena is sitting on top of Hank, which means that there's a contact force of Xena on Hank. There is another contact force of Xena on the floor, so she's touching the floor. There's also a contact force of Hank on the floor. And then, of course, Hank is touching Xena, so there's a force of Hank on Xena. If you think about non-contact forces, there's a lot of gravitational interactions going on because all of these objects have mass. The Earth is exerting a gravitational force on Xena, on Hank, on the floor. Likewise, you can talk about the opposite way. You can think about the gravitational force that Xena is exerting on the Earth. Xena is exerting gravitational force on Hank. Anything that has mass exerts a gravitational force on every other thing that has mass. I will give you one note here. Typically, we don't bother to consider these forces between objects that have small masses, the gravitational forces between them. Like the force of Xena on Hank is so small compared to the gravitational force of the Earth on Xena or Xena on the Earth. So we really typically only look at gravitational forces between an object and another object where one of these objects at least is very massive. So the other ones, it's just too complicated. And honestly, they really are so small compared to the massive pull, the gravitational pull of a large object on even a small object. So I'm not going to include any of those in any of the next examples that we do. And that's why. So here's just a few of the forces. I have basically the picture is that there's a lot of interactions going on. And all of these forces can contribute to the motion of all of the objects that are in my system. And so we have to keep track of all of these forces. That's why we give them names. We put these subscripts on there so that we know the direction, the magnitude of these forces, and then who is exerting it, and then what is it being exerted on. We have to keep track of all of this stuff. And that's the point of a free body diagram. It keeps track, it gives you a graphical representation of all of the forces acting on a particular object. So a free body diagram, I often abbreviate it as FBD. Some instructors might call it a force body diagram. Same thing. That's probably why we always just abbreviate it as FBD. If it helps you remember, force body diagram, it is a diagram that shows all of the forces acting on a system. So let's just back up for a second here and talk about what is a system? How do I know what my system is? Well, you get to choose your system, and you'll gain intuition for what you want to be in your system and what you don't want to be in your system with practice and when you get deeper into physics. At the moment, I'm just going to tell you what your system is. But a system, basically, it's a collection of objects. It could just be one object. It could be a lot of objects. But basically, if you can imagine kind of putting a bubble around these objects or this particular object, and that's your system, then anything that's not in that bubble is external to your system. We call it the environment. The environment can act on your system. Your system can interact with the environment. So you just have to define what is in your system, because that's going to dictate which forces appear on your free body diagram. And just to reiterate, this free body diagram, it's not a sketch of your problem. You should also create a sketch of whatever problem you're working on. You should draw a picture, show some distances, like label things on there. A free body diagram is a supplement to that sketch. It's a completely different tool that we use to just analyze the forces that are acting on our system. So I'm going to give you some rules. If you can learn these rules, you'll be at a good level to start drawing free body diagrams. The first rule is that you're just going to represent your system as just a little dot. We don't care about the dimensions of your system and showing all of the details. We just assume we can like crunch your system down to this little dot. All of the mass of your system is located at this kind of dimensionless dot. Sometimes I make my dot a little bit bigger, depending on how many forces I have acting on it. I might need to make my dot a little bit bigger so I can fit all of these forces acting on my system. Then we want to draw the force vectors. We're going to draw them like arrows, just like every other vector we've ever drawn. It's like an arrow where the length of the arrow represents the magnitude of the force. The direction of the arrow tells me about the direction of the force. And we want the tails of the arrows to be located near the dot so that all of our force vectors are pointing away from the dot. This is just a convention to make your diagram look consistent with other people's diagrams. So just try to do this as much as you can, just so that your diagrams look consistent to other diagrams. Then you want to label your force vectors with this subscript notation. So give it a name and then use these subscripts to tell you what is exerting the force and what the force is exerted on. And if you're careful, all of your second subscripts for all of the forces should be the same, because you're only drawing forces that are acting on your system. So all those second subscripts should be the same if you've drawn your free body diagram correctly. The last thing to do is just remember to go back and double check that you didn't draw any vector that's not a force. And so make sure all of your vectors are forces. And then after you've done that, make sure that all of these forces are acting on your system. They're not forces that your system is acting on the environment. It only can be forces acting on the system. Please learn these rules. These are the very, very basic things about free body diagrams. This is not even like the meat of like learning the physics. The real physics of it is actually identifying the forces within a picture. I'm not even making you guys do that. I'm just telling you about how to actually draw the diagram once you know what the forces are. So we're removing the real physics of it. I'm just giving you the rules of how to make your diagrams drawn consistently. So please learn these rules. It's not a lot here. And when you get to Physics 1, you'll be one step ahead of everybody else who hasn't learned these basic rules. Some very common mistakes that I see over and over and over again. I just want to give you a heads up so that maybe you will not fall into these same traps. Again, make sure that you're only drawing forces. I see a lot of people draw acceleration, velocity, displacement. They just try to add everything, every detail of the problem onto their free body diagram. That's not what this is. We are only drawing forces on these diagrams. Make sure that you are only drawing forces that are exerted on your system. So use those subscripts and make sure that every second subscript represents your system. So it's the force of the earth on the system, and the force of the floor or the dog or whatever. It's always acting on whatever is in your system. So external forces should be drawn on the free body diagram. Any forces that are describing interactions within items within your system. So let's say your system has a lot of objects within it. If one object is interacting with another object within the system, that's what we call an internal force. And you don't need to put those on a free body diagram because we only want to put forces that are external to the system that are acting on the system. And then the other problem that I see a lot is people not drawing their directions correctly. We want the tails of these vectors to be at the little dot that represents your system. So you can always pick up and move a vector however you need it. So if you're force, if you know like gravity is, pulling you down, you just want to make sure you move that vector so that the tail of the vector is at the dot that represents your system. So let's do an example here. Here's go back to our dogs. So there's Xena sitting on Hank, who's sitting on the floor on the surface of the earth. So I have drawn a bunch of force vectors, all of them that are within this picture. So it's not necessarily just, I haven't defined my system yet. So I've just kind of drawn everything for you. And this is the notation that I've used for each of these subscripts. You can understand what each of these subscripts means. There's Xena, Hank, Earth, and the floor. So tons of different vectors here. Now I want to, based on all of these vectors, now let's actually define our system and draw a free body diagram for a particular system that we've chosen. So let's say right now that we're going to draw a free body diagram where our system is Xena, okay? So if you look at all of these forces, we want to identify the forces where it's something exerting a force on Xena. So these subscripts tell us which of these forces should be included on this free body diagram. Any vector that has X as the second subscript is something that we would include on a free body diagram for our system in which Xena is the system. So just looking at these subscripts, I can identify these three forces right away. These are the three forces that should be on a free body diagram for just where our system is just Xena. So I've just kind of copied those forces over here. Now I'm going to draw my free body diagram. I draw my dot that represents my system. Now I draw each of these force vectors where their tails are near the dot. And then I give them names with these subscripts to tell me who originated the force and what was it acting on. If you look at all my subscripts, they all end with X, which represents Xena, which is my system. So here's a properly drawn free body diagram of where my system is just Xena. All right, what if we do the same thing, but now I've changed my system. Now I want to identify a free body diagram where my system is Hank. All right, well, I just go back to that picture where I had all of those forces identified. I had all those subscripts written down. Now I just look at the forces where it was something exerting a force on Hank. So H would be my second subscript. So going back to that picture, I identified three more forces where each of the second subscripts is H, representing Hank. And so now I, again, draw my system as a little dot. I draw my force vectors on there with the subscripts. Double check that I didn't draw anything that's not a force. Make sure that everything is always acting on the system. So all of my second subscripts are Hank. And there's a free body diagram for Hank. All right. What if now I consider a system in which the system is comprised of Hank and Xena? So it's not just a single object in my system. Now it's two things that are in my system. Okay, well now I go back to that original picture. I look at all of those force vectors and I can pluck out every single one of them where a force was being exerted on Hank or on Xena. So we already did the free body diagram for Hank and Xena, and they each had three forces acting on them. So basically I'm going to take all of those three forces. So I should have 6 total forces that are describing an interaction where something is exerting a force on either Hank or Xena. So here are those 6 forces. I copied them down for you again. And technically all of these forces can go on our free body diagram. You might notice though, that there are 2 forces that are internal to the system. They are only describing objects that are inside of the system. If you look at these 2 forces right here, where it's the force of Hank on Xena and the force of Xena on Hank, those are internal forces. They're not describing something that was external acting on the system. They're internal. So I am not going to put those on my free body diagram. I'm only going to include the forces that are external to the system. So that's my free body diagram for the system in which it's comprised of Zena and Hank. So you can notice that all of the second subscripts are either X's or H's, because those were things that were in my system. And all of the forces that I've drawn are coming from or originating from things that were external to my system, which is why I did not include these two internal forces. If you put them on there, it's not technically wrong, it's just unnecessary. If you notice, those two forces are going to cancel out. One is going up and to the left with exactly the same magnitude and direction as this one is going down and to the right. So when you're going to apply and use this to actually solve a problem, those forces aren't going to contribute to the motion of your system. That's why it's just unnecessary to put them on the free body diagram. So I'm just telling you, don't do it. It'll mess you up, because if you don't put all of them on there, if you miss one, if you forget it, then it's going to mess up the rest of your problem. So that brings me to the last point here about why we're using, or what we do with a free body diagram after we've drawn it. The main point is that there is something called Newton's second law of motion, which says that the net force, or the sum of all of the forces, and remember forces are vectors, so it's the vector sum of all of the forces, is equal to the mass times the acceleration of your system. So if you add up all the forces that are acting on your system, that is equal to the mass times the acceleration of your system. That's basically the big picture. I'm not gonna, that's really a job for Physics 1 to let you, use this equation and show you where it came from. But this is why we draw the free body diagram, so that we can identify all of the forces that are acting on a system, so we can visualize it. It's a graphical representation. We can see the directions and magnitudes of all of these forces, which allows us to then add all of these force vectors. And we're going to do so very carefully using all of the rules of vector math that we've learned so far, making sure that we either use graphical vector addition, where we add them up tip to tail and find the resultant, or you can put them in component form and then just add them up using their components. Whatever way is your favorite or the fastest for your job, choose that. Just make sure you're not violating any rules of vector math. And then you just set that sum equal to mass times acceleration vector, and you can solve for whatever unknown thing is happening in this problem. But that's the idea. We use this free body diagram to identify all the forces so that we can add them up. That's it. And now you know all of the very basic things about how to draw a proper free body diagram.